Swayam Prabha. Digital India. Educated India.
Hello my dear students, welcome to Swayam Prabha. Course title Pharmaceutical Organic Chemistry 2. Lecture title Polynuclear Aromatic Hydrocarbons. Module number 4, lecture number 9. This course, it is as per Pharmacy Council of India syllabus, that is PCI syllabus, and it is beneficial for second year B Pharma students. Myself, course coordinator, Mr. Dhamak Vikrant Murlidhar, affiliated to Savitribai Phule Pune University. Name of academic expert, Dr. Sunil V. Amrutkar. Project name DTS Swayam Prabha, sponsored by MHRD, New Delhi. We will see firstly learning outcomes of this session. Learner will be able to understand the concept of polynuclear aromatic hydrocarbon with its classification. Learner will be able to understand IUPAC nomenclature of some of an examples of an polynuclear aromatic hydrocarbon. So in this session we will be seeing only 3 polynuclear aromatic hydrocarbons, and in the remaining session or in the next lecture we will see 2 more polynuclear aromatic hydrocarbons and some relevant derivatives of this IUPAC nomenclature. Learner will be able to understand the synthesis and reactions of polynuclear aromatic hydrocarbon. Learner will be able to understand uses of polynuclear aromatic hydrocarbons. So for what purpose they are being utilized on the commercial scale, and that is the need to study this polynuclear aromatic hydrocarbons. So the contents for this session: firstly, introduction to polynuclear aromatic hydrocarbon, and also the classification of this polynuclear aromatic hydrocarbons and why they are said to be polynuclear, and what is the role of an aromatic ring in it. After that we will see nomenclature of naphthalene or diphenyl methane and triphenyl methane. So there are almost 5 polynuclear aromatic hydrocarbon in a syllabus, and from this we are conducting 3 examples in this session. After that we will see synthesis method of naphthalene, diphenyl methane and triphenyl methane, and there are some reactions of naphthalene, diphenyl methane and triphenyl methane. In between that we will also see reactivity of an naphthalene. So Why that only alpha product it has been forming rather than beta, or why it is predominant. Also we will see the reactivity and some resonating structures of an naphthalene. And lastly we will see uses of naphthalene, diphenylmethane and triphenylmethane. Most of they are utilized for dye purposes, and we will see individually, and all these contents we will see individually for individual classes. So let's first see what is polynuclear hydrocarbons. Hydrocarbons are made up of two or more benzene rings. So here it deals actually with an aromatic polynuclear aromatic hydrocarbons. So when it comes to only an polynuclear hydrocarbons, so it may be not an it is not having an aromatic ring, but we are dealing with a chapter or a module that is related with an polynuclear aromatic hydrocarbons. So the hydrocarbons are made up of two or more benzene rings fused together, or isolated benzene rings, or non-benzoyl nucleus are called polynuclear hydrocarbons. Not just only polynuclear hydrocarbons, but polynuclear aromatic hydrocarbons. Though it is not having an benzene structure, but there are some rings which do have an aromatic structures. So we will see some of an representative examples from this polynuclear aromatic hydrocarbons. So one of them, that is naphthalene. Two benzene rings, they have been fused. After that we will look phenanthrene. So phenanthrene and anthracene, they are having an aromatic ring, number of aromatic ring 3. But only the difference between this phenanthrene and anthracene is that the anthracene, it is having a linear chain of an aromatic ring, or linearly they are been arranged, and phenanthrene, it is not a linear one, or we can say it is a non-linear one. After that, diphenylmethane. So name itself indicate having two phenyl rings, and methane is a adjoining moiety between two phenyl rings. After that, trimethylphenane, similarly as dimethylphenane, it is having an 3 phenyl, so triphenyl, and in between having an methane. So this methane, it is connected with this phenyl, and so it is said triphenyl methane. So these 5 structures, or these 5 compounds, we will be seeing in this polynuclear aromatic hydrocarbons as an representative examples. Now we'll see the classification of an polynuclear hydrocarbons. So first one is benzonoid, and distinguishing to it, it is non-benzonoid. So benzonoid, name itself, it is indicating that it might be having an benzene aromatic ring, and non-benzonoid, it is not having an benzene structure. Though it is not having an benzene structure, but it is aromatic, because all the carbons, they are been sp2 hybridized, they are planar, and number of an pi electrons, it is 10 in case of an azulene, so it is an aromatic structure. After that, benzonoid, it has been classified into 2 parts, that is isolated and fused ring. So isolated means benzene ring, it has been separated by some means or by some bonds, or having some moieties in between, like we have seen the structure of an trimethylphenane and dimethylphenane. So this one, it is a structure of an biphenyls fused. Again, there are 2 categories in case of infuse. So one is linear and second one is angular. So naphthalene, it is a linear structure, as It is straight, so it is linear, and angular, it means an phenanthrene. So phenanthrene, it is non-linear, so it is said to be an angular. So this is an classification of an polynuclear aromatic hydrocarbons. Now we'll see IUPAC nomenclature. IUPAC nomenclature for naphthalene and its derivative. The monosubstituent naphthalene derivatives are usually designated by the prefix alpha and beta. In IUPAC numbering system begins with the number 1 at the alpha position. So this is a structure of a naphthalene. Two benzene ring, they have been fused. So from alpha, numbering starts. So alpha, beta, gamma. Usually we come across these two structures in case of in this course, that is alpha and beta substituted. So numbering starts from an alpha position. So as it has been said over here, that from an alpha position, number 1 starts, 2, 3, 4, and this fused carbon, it is not given number because it does not have any kind of an substitution. So it has been neglected because there are all 4 bonds of an carbon which does not allows any type of an substitution, because there is no hydrogen over here, so it has been neglected. And after that 5, 6, 7, 8 respective. So this structure generally it is called alpha naphthol. As per IUPAC, it is said to be an 1 naphthol, and OL, it is representing OH or alcohol at the end. And due to this alcohol substitution or OH substitution, it is indicating OL at the last. So general name alpha naphthol and IUPAC name, that is 1 naphthol. General name, that is beta naphthylamine, because amine it has been substituted at an beta position. As you can see, this is the second one is in beta position. So IUPAC, as per IUPAC, we will say it is an 2-naphthylamine. After that 1,8-dibromonaphthalene. So at first position and 8th position, as here you can see that first position and 8th position, it has been substituted by 2 bromine, so dibromonaphthalene. So now we will see some properties of a naphthalene. Naphthalene is colorless solid which forms shining flake crystals. It is very volatile and sublimes slowly at room temperature. Naphthalene gives aromatic electrophilic substitution reaction, as we will see in chemical reactions. The product of monosubstitution is either alpha or beta depending on the conditions. And in case of an alpha and beta substitution, as we have seen, there is only 2 type of an substitution, most often alpha and beta, but alpha always predominates. And why does it predominates? Only there is an alpha substitution most of the time and not beta, but for an harsh condition it may be an beta. So we will come across such type of reaction, that is alpha as well as an beta. And also we will see why the reactivity at an alpha position it is more compared to a beta position. Now we will see synthesis of a naphthalene and why that alpha beta predominates. We will see when we come across an chemical reactions of this naphthalene. So the first method of synthesis of a naphthalene, it is from coal tar. Naphthalene is most abundant single chemical compound present in coal tar, so it is almost 10%. The middle oil fraction, having an almost temperature 170 to 230 degrees Celsius of an coal tar, chilled, and after chilling it forms an naphthalene crystals. These are separated by centrifuging. The crude crystals are melted and treated with sulfuric acid to remove basic impurities. The crystals are then washed with aqueous sodium hydroxide to remove phenol and excess sulfuric acid. So why it has been washed with an sodium hydroxide? Because it removes an acid by neutralization. Sulfuric acid, it removes an sulfuric acid by neutralization, and in case of an phenol, it forms an salt with an phenol, and due to which the phenol it has been removed. And finally, the naphthalene is distilled to get a pure product. Synthesis of naphthalene from petroleum. The middle distillate of petroleum on catalytic cracking and catalytic reforming yield naphthalene and methyl naphthalene. Methyl naphthalene on heating about 600 degrees Celsius in presence of an hydrogens are dealkylated to give naphthalene. So this is how it happens, that alpha methyl naphthalene or 1-methyl naphthalene in presence of an hydrogen at 600 degrees Celsius, it forms a naphthalene, and also it gives an hydrocarbon, that is methane. It is an aliphatic type of an hydrocarbon. Synthesis of naphthalene from 4-phenyl 1-butene. 4-phenyl 1-butene is passed over a red hot calcium oxide to form naphthalene. So this is structure of an 4-phenyl 1-butene. As we can see, it is an phenyl ring and having 4 carbons, and these 4 carbons, it is the double bond, it is at the first position, so it is given over here 1, and phenyl ring, it is at an 4th position as per the butene numbering 1, 2, 3 and 4, so it is said to be an 4-phenyl 1-butene. So this 4-phenyl 1-butene, it is cyclized, and after cyclization it forms a naphthalene, giving away and hydrogen gas. So it is also one of an indication that of an completion of an reaction, hydrogen gas it is produced at the end, and which shows that, or which indicates that naphthalene has been formed. Synthesis of a naphthalene. So we will move towards the next method, that is 4-phenyl 3-butanoic acid. As again you can see that butanoic acid, and at 3rd carbon it is having a double bond, so it is butanic acid, and at 4th position, at 4th carbon, it is adjoined to an phenyl ring, so 4-phenyl. After reacting with an concentrated H2SO4, water molecule it has been removed and it forms an cycle, and this cyclization, it has been substituted by OH, and to reduce this OH or to remove this OH, it has been treated with an zinc, and as soon as it has been treated, it forms an naphthalene at the end, forming an zinc oxide. After that synthesis of an naphthalene, so one of an important method, that is Haworth synthesis. Benzene, it is treated with succinic anhydride in presence of an aluminium trichloride. So such kind of an reaction, it is carried at an dry conditions. Usually the reactions, they are carried out in round bottom flask and condenser, but beyond that, it is having some special conditions whenever we are doing any such kind of a reaction with this Lewis acid, that is AlCl3, because it is highly water loving, and when it comes in a contact of an moisture, so it becomes an inactivated. So to remain water free or moisture free reaction condition, the condenser whatever we are using for in this reaction, so it has been either it is having an guard tube of an calcium chloride, or either it is having an argon type of an balloons, so that the moisture present in between, it has been sucked out or it has been purged out, and due to presence of an such type of an gas or this calcium chloride has an ability to remove the moisture from a reaction, and that is why AlCl3, that is Lewis acid, it does not deactivate, but as soon as it comes in contact with water, it does deactivate. So for this type of an reaction, whenever there is an AlCl3, that is Lewis acid, so such type of reactions, they are carried always in dry conditions, so then only we can get a good yield. But if conditions are not maintained, so either there will be very less yield or there will be no reaction. It forms an intermediate, that is benzoyl propionic acid. After that, it has been reduced. So particularly reduction of such kind of a reduction, whenever we come across the such kind of a reduction, that is zinc amalgam, we can say. So zinc, it has been alloyed with an mercury, and in presence of an acidic conditions, it forms it only reduces and double bond, or we can say carbonyl type of an double bond, and it forms an gamma phenyl butyric acid. After that, for cyclization, hydrofluoric acid, it has been utilized, and similar type of a reaction that has been carried out to reduce this carbonyl. So this alpha tetralone, now it has been reduced. So particular this reduction with zinc amalgam in acidic condition, particularly it reduces only an carbonyl, and it forms an tetralene, and this tetralene, it has been heated in presence of an PD and carbon dioxide, and now it forms an naphthalene. So it is quite lengthy process, but it is one of an important synthesis method for an naphthalene. Before moving towards chemical reactions of a naphthalene, one should know why this alpha product predominates in naphthalene and why not beta? So oftenly it has been seen that there are two types of an substitution, alpha or either beta, but alpha predominates. In electrophilic aromatic monosubstitution of a naphthalene, alpha product is formed in the preference to beta carbon. This is understood if we examine the intermediate carbonium ion. The two resonance structures can be written for the intermediate carbonium ion obtained from attack at alpha position without involving other ring, whereas only one structure is possible for substitution at beta carbon. If we see the structures of an alpha position of an alpha attack of an electrophile, so we can get two types of this resonating structures, but there is no involvement of an further ring. So just we have considered here only two structures of an first ring or two carbocations of an first ring. So here you can see that it is forming and carbocation at carbocation of an two resonating structures, and as soon as the electrophile it comes, the pi bond breaks, and this pi bond it breaks and shifts an electron towards an first carbon, and due to which second carbon it becomes an electron deficient, and now here you can see that second carbon it is an electron deficient, and after that the pi electrons are being shifted towards an second and third carbon, and now fourth carbon it becomes an electron deficient, as we have seen in case of an benzene also. So if you remember that shifting of an electrons, so it takes place for to resonate the structures and to make the structure stable. Now coming towards an beta position, if electrophile it attacks at a beta position, so there is only one type of an carbocation it has been formed. So there is no another carbocation formed, because here it cannot now shift towards another carbon, as we are not considering a second ring and just for the first ring, so there cannot be any more resonating structure, and that is why only alpha carbon or alpha products they are been formed and not an beta products. Beta products are formed but at an harsh conditions only. But alpha it predominates because it is having two resonating structures. As the resonating structures increase, the stability of any molecule does increase. But beta it is not having any pi bond closer to it for an exchange. So this bond it does not break because it is intact with another fuse ring. If there is by an sequence it is having an pi bond, then only pi electrons will be shifted, but it does not happen, and due to which there is only one carbon which is having an carbocation, and that is why alpha predominates on beta because of resonating structures. Now we'll see reactions of an naphthalene. So first reaction, that is halogenation. Naphthalene reacts with chlorine and bromine in solution to form alpha bromo naphthalene. And this it has been carried out in carbon tetrachloride. Naphthalene with an halogen, bromine or chlorine, and it has been heated by using carbon tetrachloride as a solvent, and it forms an bromonaphthalene, that is alpha bromonaphthalene, as we have seen that alpha product predominates on beta, so that is why alpha we get an product. Second reaction, that is of a naphthalene, it is nitration. When warmed with mixture of concentrated nitric acid and sulfuric acid, naphthalene forms an alpha nitronaphthalene. Structure of a naphthalene, and it is warmed just at 50 degrees Celsius. So we require H2SO4 also, because without it nitronium ion it is not formed, and it gives an alpha nitronaphthalene. After that next reaction, that is sulfonation. On treatment with concentrated sulfuric acid at 40 degrees Celsius, it yields alpha naphthalene sulfonic acid, and at 165 degrees Celsius it yields beta naphthalene sulfonic acid. The structure of a naphthalene, just it is warmed at 40 degrees Celsius, it forms an alpha naphthalene sulfonic acid, and when it is having a more harsh condition, such as we have discussed earlier also, why only alpha product predominates and why not beta, it is also giving a beta product, but the conditions are some harsh, and so now it forms an beta naphthalene sulfonic acid. So from this reaction you can understand that there is not only an alpha type of an product that we obtain, we also obtain an beta type of an product, but the temperature difference, they are quite, means we can conclude from it that when the reaction conditions are normal, at that time alpha product it has been formed, and when the reaction conditions they are beyond the normal, in that case we get a beta product. Important reaction of a naphthalene, that is Friedel-Crafts acylation. Naphthalene reacts with acetyl chloride or benzoyl chloride and aluminium chloride in CS2 to give alpha acetyl naphthalene. If nitrobenzene is used solvent, a beta product has been formed. So one case is also that to form and beta product we require some type of an solvents that which promotes an beta product. So solvents like an nitrobenzene. So in presence of an aluminium trichloride and acetyl chloride, it gives an alpha acetyl naphthalene. And in presence of an nitrobenzene, so nitrobenzene plays an important role over here. If nitrobenzene it has been utilized, then only it forms an beta type of an product. And also you can see now the reaction condition. So for alpha it is minus 15 degrees Celsius, and for beta it is 25 degrees Celsius. So it is quite big gap. Again we can understand from this that alpha it is formed at normal temperatures and conditions, but for beta product it requires some special conditions and beyond the limit conditions, and also some solvents like nitrobenzene which promotes formation of an beta product. After that, reduction of a naphthalene with sodium and alcohol forms 1,4-dihydronaphthalene. So 1,4-dihydronaphthalene, it is because at first position, so as we have seen in case of an IUPAC nomenclature, first position and fourth position. So at first position, it is now having, it has been reduced and now it is having an two hydrogens. As this bond has been reduced, or these pi electrons are being converted to now a sigma bond, and the hydrogen, it has been replaced at 1 and 4th position. So that is why it is dihydronaphthalene. And when a catalytic hydrogenation it takes place, it gives 1, 2, 3, 4 tetrahydronaphthalene, that is called tetraline, or decahydronaphthalene, and it is also called decalin, depending on the catalyst used. So naphthalene, when it has been heated with nickel and hydrogen gas, it forms tetraline. And when the conditions are different, when it has been heated with platinum and moles of hydrogen, it is also higher compared to this nickel type of conditions, and now here it forms an decalin. So from this also we can understand that by using different conditions, so different type of an reduced form, they can reduce type of structures we can get, or different type of structures do we get after reduction by using different conditions. After that, reactions of an naphthalene on mild oxidation by chromic acid in acetic acid forms 1,4-naphthaquinone. And 1,4-naphthaquinone, why it is? Because now it is having an carbonyl or ketone, we can say ketone at 1 position and 4th position, so that is why it is called naphthaquinone. And upon oxidation with air and vanadium pentoxide, it yields phthalic anhydride. So by using different conditions, we can get several products of an oxidation. Now we'll see uses of naphthalene. Everyone might be knowing that we are having some moth repellent, and this moth repellent are nothing but a naphthalene balls. So for daily household, we are using in basins, bathrooms, this naphthalene ball as a moth repellent. Naphthalene is used as moth repellent to protect woolen goods also. Naphthalene is used for commercial production of phthalic anhydride. Naphthalene is used for making of an alpha naphthol, that is insecticide, and beta naphthol, that is tanning agent. Naphthalene is used for manufacturing of dyes, explosives, and synthetic resins. So dyes, it is one of an important use of an naphthalene. So some of an naphthalene derivatives, they are dyes. Naphthalene is used for manufacturing of drugs such as propranolol. It is anti-hypertensive. After that, antifungal drug, that is tolnaphthate, and after that nefazolin. So these are some of drugs which are having basic ring of an naphthalene as well. they are not directly nowadays not directly naphthalene it has been used, but naphthalene, it is a basic moiety in it, and from that basic moiety the reagents for a starting material for such kind of drugs they have been prepared. Now we'll see IUPAC nomenclature of two more molecules from this class, that is polyaromatic hydrocarbons. So one is diphenyl methane and second one is triphenyl methane. So for an IUPAC numbering, so first ring, that is first phenyl ring, so it has been numbered, and second ring it has been numbered with a dash. So it is for an indication, so on which ring substitution has been taken place, and this methane in between, so it is numbered as in 7. After that, triphenyl methane, so similar in case of an triphenyl methane, so one ring it is numbered, second ring it is been numbered with a 1 dash, and third ring it is numbered with a 3 dash. Say suppose substitution there are 5 position of an each ring, so it will be 5 dash and again 5 double dash, and after that triphenyl methane. So this is how it has been numbered. Now we'll see each class individually. That is now triphenyl methane. Diphenyl methane, it has been synthesized by Friedel-Crafts reaction. Benzyl chloride benzene in presence of an aluminum trichloride to give diphenyl methane. So this is structure of an benzyl chloride. Benzene and benzyl. So benzyl, when it is referred benzyl, so it is having a CH2 in front, and if not this CH2, if it is only limited up to this ring having one bond, so it is said to be an phenyl ring, and when it is having a CH2 in front, it is said to be an benzyl, and now it becomes benzyl chloride. And when it has been reacted with an benzene and aluminum trichloride, it forms an diphenyl methane. After that, synthesis of an diphenyl methane from benzophenone. So it is one of an type of an rearrangement reaction, that is Wolff-Kishner reduction. So benzophenone, it has been reduced with the help of an Wolff-Kishner type of an reduction reaction by using zinc amalgam, which gives diphenyl methane. And also we have seen earlier that what is this zinc amalgam, it reduces particularly an ketonic functional group. So it is very simple reaction of an reduction of an benzophenone to diphenyl methane. Synthesis of diphenyl methane from toluene by oxidizing toluene with KMnO4. So it has been oxidized to benzoic acid, and after oxidation of an benzoic acid, it is reacted with SOCl2. It forms an benzoyl chloride, and after formation of an benzoyl chloride, it has been reacted further. As such, we have seen in case of an Friedel-Crafts reaction. So benzene, it has been substituted on this benzoyl chloride by dehalogenation, and now it forms an benzophenone, and this benzophenone, it can be also reduced particularly by this Wolff-Kishner type of an reduction reaction by using hydrogen hydrate in basic media. And it forms an diphenyl methane. Now we'll see reactions of an diphenyl methane. So first reaction, that is halogenation. Diphenyl methane when halogenated with chlorine gives 1 benzyl 4-chlorobenzene. So diphenyl methane reacted with an chlorine in presence of an CCl4 and it gives 4-chlorobenzene. So benzyl, it is due to this phenyl having an CH2 in between, and at 4th position chlorine it has been substituted, so that is why 4-chlorobenzene. Reactions of diphenyl methane. So now we will see nitration, as we have seen the nitration in earlier some chemical reactions, that it requires an nitric acid as well as an sulfuric acid to form an nitronium ion. So diphenyl methane when treated with and nitric acid and sulfuric acid, it gives 1 benzyl 4-nitrobenzene. The structure of an diphenyl methane and nitrating mixture, that is nitric acid and H2SO4, generating a nitronium ion. And so such kind of an electrophilic aromatic monosubstitution type of a reaction we are going through. So it forms an nitro product at 4th position. Now further we will see cyclization of an diphenyl methane. So diphenyl methane when heated at extreme in a hot rate tube, it gives an cyclized product. So it has been heated at almost 450 degrees Celsius and it gives an cyclized product. So the both rings, they form one more new bond, and this such kind of a reaction, it does not require any type of a reagent. So it comes under category of an pericyclic type of a reaction. Now we'll see oxidation of an diphenyl methane. So diphenyl methane when oxidized with potassium permanganate gives benzophenone, as we have seen the reverse reaction in the synthesis of an diphenyl methane, that benzophenone after reduction it gives an diphenyl methane, and when diphenyl methane it has been oxidized, it forms an benzophenone. So this oxidation is carried out in presence of an oxidizing agent, that is KMnO4, and now it forms an benzophenone. Now we'll see some uses of an diphenyl methane. Diphenyl methane is widely used in synthesis of luminogens for aggregation induced emission. It is used in preparation of a polymerization initiator, diphenyl methyl potassium. So the potassium salt of this diphenyl methane, it is used as an initiator for an polymerization. Diphenyl methane derivatives are a group of drugs used in treatment of variety of emotional and mental disorder characterized by tension, anxiety and agitation. So there are lot many drugs in case of an CNS. So they are having a basic ring of an diphenyl methane, and also in case of an ANS we can see such kind of structures having a basic ring of an diphenylmethane. Some derivatives are used as antihistaminics like cyclizine and hydroxine. Lot many drugs which shows an antihistaminic activities also shows an anticholinergic properties. So similar type of an arrangement, or we can say similar type of an derivatives, they does have, and having a basic moiety, that is diphenylmethane. So some of an diphenylmethane derivatives also shows an anticholinergic property, and this anticholinergic property of a drug, it is due to that it is having a benzene ring at the periphery, so it shows an anticholinergic type of an properties. First reaction, that is Friedel-Crafts reaction. So triphenylmethane, it has been synthesized by Friedel-Crafts reaction. So Friedel-Crafts reaction, how important it is, you might have realized, because in lot many structures till yet we have seen the Friedel-Crafts reaction. It is been a synthesis method for almost all the moieties. 3 moles of benzene react with a chloroform in presence of an aluminium chloride, gives triphenylmethane. So this benzene and Lewis acid, that is AlCl3, in presence of an chloroform, it gives an triphenylmethane. So it is a simple reaction, and this chloroform, it acts as an mediator for this attachment of an phenyl ring, and it forms an 3 moles of an HCl plus. Now we'll see reactions of an triphenylmethane. So first one, that is halogenation. Bromine reacts with triphenylmethane, gives triphenyl bromide. So it is one of a simple reaction, just replacing and hydrogen. And it forms a triphenyl bromide. After that, next reaction, that is a nitration. So triphenyl methane is reacted with nitric acid and sulfuric acid, which gives rise to tris. So tris means 3 nitrophenyl methane. So when it is bis, it means 2, and when it is tris, it means 3. Nitrating mixture, and this nitrating mixture, now it gives a nitronium ion, so which has been substituted at 4th position of an each phenyl ring, forming an 4 nitrophenyl, so 3, so that is why tris. Now we'll see some uses of an triphenylmethane. Triphenylmethane is used as dyes in textiles such as wool, silk and cotton. Triphenylmethane derivatives have poor resistance to light and to chemical bleaches, and are used chiefly in copying papers, in hectograph and printing inks. Triphenylmethane derivatives such as malachite green and crystal violet are used in staining of an microorganisms. So you might be knowing, in case of an microbiology, so for gram staining, negative staining and positive staining of an bacteria, we require such type of an reagents. Now we'll see a summary of this session. So starting with a concept of an polynuclear aromatic hydrocarbons, we have seen the classification, and there are two main classes, benzonide and non-benzonide. And after that, we have seen further classification. After that, we went through an IUPAC nomenclature of each aromatic polynuclear aromatic hydrocarbons and numbering of them. The structure of a naphthalene having a position alpha and beta. So you might be very familiar with alpha naphthol and beta naphthol. And numbering of an naphthalene. After that, numbering of an diphenylmethane. And after that, numbering of an triphenylmethane. So we have seen all these things in details. Synthesis of naphthalene. So naphthalene, it has been synthesized from coal tar. So we have seen that how distillate it has been separated. After that, from petroleum. So one of an product given by an petroleum, that is alpha methyl naphthalene, and it has been hydrogenated at higher temperature. After that, from 4-phenyl 1-butene, it has been cyclized with calcium oxide. After that, 4-phenyl 3-butanic acid, again it has been cyclized with the help of zinc and H2SO4. And after that, we have seen such kind of a reaction. So it is nothing but an Avort synthesis. Succinic acid and benzene react, and there are multiple steps. So we have just mentioned over here last product, that is naphthalene. Summary of reactions of naphthalene. So when it has been halogenated, it is substituted at first position, forming an alpha bromo naphthalene. When it has been nitrated, again same is the thing, that it has been substituted at an alpha position or first position. After that, sulfonation, sulfonated at first position. Sulfonated at beta position. So here you can see the difference, that we can get both the product, that is alpha and beta, but conditions should be different. So for alpha, it requires an minimum conditions, or easily we can get a product of an alpha, but for an beta it requires an harsh conditions. After that, Friedel-Crafts alkylation we have seen. Friedel-Crafts alkylation also gives a different type of an product, that is alpha and beta. So here the solvent plays an important role. After that, reduction with the sodium and ethanol. So it forms 1,4-dihydronaphthalene. So from overall we can understand that beta alpha product, they are readily being formed, but for an beta product we require some drastic conditions of an chemical reaction, so that we can also get a beta product. So more oftenly we just get alpha, and after that we get an beta. So beyond that we does not get any type of a substitution of a product. And lastly, we have seen oxidation. So carbon number first and carbon number fourth, it has been oxidized. After that, we have seen reactions of diphenylmethane. So it is nothing but Friedel-Crafts type of a reaction, that is benzyl chloride react with an benzene in presence of an Lewis acid. After that, reduction of an benzophenol by zinc amalgam. After that, toluene. So from toluene it is again a multi-step type of an reaction. Just we have mentioned over here a starting material. After that, now reactions of an diphenylmethane. After halogenation, it forms an chloro-derivative. After nitration, it forms a nitro-derivative. Nitro-derivative, it is at a 4th position only. After that cyclization, so it gives a cyclic product, and after that oxidation, it gives an benzophenone. So here we have also seen by reduction of an benzophenone, we does get an diphenyl methane, and from oxidation of an diphenyl methane, again we can get the same product, that is benzophenone. Reaction and synthesis of triphenyl methane. So benzene, 3 moles of an benzene, it is reacted with chloroform. So it is type of an Friedel-Crafts type of an reaction. Halogenation, reaction of an triphenyl methane gives an halogenated product, that is. After that nitration, so it gives an tris type of an product. So 4th position of an each phenyl ring, it has been substituted by a nitro. We have seen some uses of some polynuclear aromatic hydrocarbons, and most of them, they are dyes. So thank you. We have completed one session from module 4, and this was lecture number 9. So in the next session, we will be completing last session of module number 4 with remaining 2 polynuclear aromatic hydrocarbons as per the syllabus.